Hello, everyone, and welcome back to another Planetarium show. My name is Jessica. I'm the director of the Planetarium, and with me tonight are some familiar faces if you've seen us before. These are two of the students who work in the Planetarium, and I will let them introduce themselves. We'll start off with the guy who's going to be leading our show tonight.
Hi, I'm Eli. I'm a physics undergraduate student at UMD.
Hi, I'm Lindsay. I'm a physics graduate student at UMD.
So, tonight we have the next edition of our exploration series where we've been taking a kind of deep dive into some popular topics. In the past, we've done Mars, black holes, dark matter, and dark energy. It's been a lot of fun. And tonight, we're going to take a close up look at the closest star to us, our sun. And Eli is going to be leading us on that adventure. And before I turn it over to him, as always, if you have any questions throughout our show tonight, feel free to leave them down in the comments. I'll be keeping an eye on those and we will try and answer them as they come up. We'll also have time at the end to answer questions as well. So, with that, Eli, it is all yours.
Okay, give me just a second. I want to make sure the
Oh, I
screen
did
share.
not turn on screen sharing. I keep forgetting. There we go.
Alrighty. Does that look okay?
It's kind of small.
Is that better?
Yes.
Sweet. Okay, let me get my presenter notes up. Okay, so welcome to Exploring the Sun. I believe the Facebook event said closest star. This is nearest star. Sorry, same difference. But I thought we'd start out by just kind of giving a general idea of what a star is before we kind of go in depth and talk about the peculiarities of our sun in particular. So stars are kind of their definition is luminous spheres of hot gas and plasma held together by their own gravity. And it is estimated that there are as many as 10 quadrillion stars in the observable universe, and they come in many different shapes and sizes, except not really for shapes because they're all spherical. But many different sizes, colors, temperatures. There's a lot of variation from star to star. So let's talk about that held together by their own gravity bit too. So stars are, like I said, these big gaseous balls whose gravity of their like constituent atoms holds them together. But you might think, what kind of maintains that structure? What keeps it spherical? That's because stars are in what's called hydrostatic equilibrium. And this just basically means that the gravity generated by all of the individual atoms, let's say in the sun in particular, which is a lot of atoms. We're looking at 10, let me make sure I pronounce this right, 10 septendecillion, which is 1 with 58 zeros atoms in it in our sun alone. So is that gravity generated by all those particles is almost perfectly balanced for a good portion of the star's life by the pressure pushing outwards from the center of the star, which is caused by nuclear fusion, which we'll talk about in the next slide. So this balance, it's just kind of a push against a pole, just basically maintains the shape of the star rather than it collapsing or blowing up or falling apart. They stay pretty rigid because that pressure pushing outwards is directly opposed by gravity pulling inwards. So another thing I want to talk about is what generates that pressure in the star, and this is a more scientific diagram than I was hoping to find, but nuclear fusion occurs in the cores of all stars. That's what makes it a star. And that includes our sun. Nuclear fusion is a really, really powerful and energetic process in which atoms are squeezed together so tightly that rather than bounce off of each other like they would do in, for example, our atmosphere, they combine to form new atoms. Our sun in particular right now is exhibiting for most parts the proton-proton chain, which is what you're seeing the diagram of here. And a lot of stars do this, and all of them do that are less massive than or just as massive as the sun. And in this process, protons combine to form one helium atom and two free protons. And it's really complex, and this diagram doesn't really do it much justice. And it took astronomers and physicists a very long time to figure this out. And part of the reason for that is the hardest part about studying stars is that we can't go touch them or, gather a sample and see what's happening. Not only would that be very painful and melt you, but they're just too far away. We can't get to them quite yet. And even when we do, which we do have a probe that's going very close to our sun, the Parker Solar Probe, like I said, it would get burned up before you could even get anywhere close to getting a good sample. So it's really amazing to think that scientists have learned everything they know about these stars just by looking at them as points of light in the sky, and also through telescopes. But so the next thing I want to talk about was how stars form. Sorry, I have to clear my throat. So it is believed that many stars, our sun included, form when large rotating clouds of gas and dust slowly compress over time due to gravity and friction between whatever's orbiting or within the gas cloud, and this makes a solar nebula that is even further compressed and flattened into a disk. At the center of this disk is what astronomers call a protostar, which is a large sphere of gas and dust that has not started fusing elements at its core, and is still kind of drawing matter from the gas around it and is slowly condensing. So after a long period of time, the protostar becomes massive enough to begin that nuclear fusion, at which point it becomes a star. That's kind of what differentiates a cloud of gas from a star. So meanwhile, the gas and dust and other matter orbiting the protostar conglomerates into planets, and that's for another episode of exploration probably, but that's where the planets come from. So another thing I want to look at is kind of how we classify stars. There are a lot of different ways to classify stars, but the most widely used methods are by color, which is indirectly by temperature, or I suppose directly, and mass. So lower temperature stars glow more in the red and the orange range of light, while hotter stars glow more in the white and blue range of light. And this color is an extremely powerful tool, because by identifying a star's color, which you can do just by looking at it, you can see what the temperature of the star is. And temperature gives way to a lot of information. So the diagram on the left shows different colors of stars and their associated temperatures. So you can see like the sun, which is about halfway down, kind of glows yellow, whitish, is about 5,000 to 6,000 degrees, while blue stars like Spica right there, you can see blue, much hotter. I mean, you can by a factor of 5 hotter than the sun just by that change of temperature. The diagram on the right is called a Hertzsprung-Russell diagram, or an HR diagram, and it's a way of classifying stars based on their color and temperature as well as the luminosity. Luminosity is pretty much how bright the star is or how much light comes off of it, and it is also a really powerful tool because it can tell us about size. Because like the larger a star is, the more surface area there is for light to come off of, the more light comes out of it, and you can kind of tell that a star that's brighter, depending on what color it is, will give off more light and it will be larger. So together, size and color tell you an incredible amount about a star. And this is just a really cool little video that kind of demonstrates how color and temperature are related using a light bulb filament, but it's very analogous to color and temperature for stars.
Using a 12-volt bulb, a power supply, and a variable resistor, you can demonstrate the different colors of stars as they glow at different temperatures. Start with the bulb glowing dimly. You'll notice that the filament is glowing faintly but red in color. Use the resistor to increase the voltage across the bulb. As you increase the voltage, the brightness and temperature increase, and the color changes to orange and then to yellow. At full brightness, the filament is glowing white hot. This demonstrates how we can use the color of a star to tell us something about its temperature. Red stars are relatively cool, white stars are hotter.
So that's just kind of a direct example right there for how color and temperature are related. I mean, you can see that as the temperature in that light bulb filament increases, it would start glowing. It'd start at red when it was colder. Well, cold is probably not the right term, but less hot. As you increase the temperature in the filament, it would start glowing red to yellow to white, and then you could almost see a little bit of blue at the end there. But I think if it were to actually glow blue like we see stars glow, that filament would be toast. So probably don't want to do that. But it looks like we have a repeat of this slide. Okay, there we go. So another thing I want to talk about is kind of the history of solar observations, because I think that's an important part of exploring the sun as well. Almost completely throughout history, humans have observed and used the sun as a calendar. Some have worshipped or deified it, and I mean, it's kind of hard to miss when you're outside. So it's a pretty prominent theme we notice in records from early civilizations. So, for example, it's believed that Celtic peoples built Stonehenge some probably about 5,000 years ago. It might have started to act as a calendar, with it oriented directly towards the location of sunrise on the summer solstice. So they would know that when the sun was rising and it appeared just through the right spot in the stones, that it was the summer solstice. So it kind of acted as an annual calendar. Um, there's some confusion about whether it began as burial ground because they found remains buried under it, but it was certainly constructed to serve as a solar calendar, at least externally. So additionally, the Pyramid of the Sun, which was built some 2,000 years ago, served as a solar marker for a pre-Columbus Mesoamerican civilization. That was also increasingly popular in Meso and Southern America. There were a lot of like pyramids and temples that would line up with different astronomical objects as a calendar, the sun being probably the most popular one of them. And these are just two examples. That you can find a lot of stuff like this. It's really impressive how accurate and how knowledgeable these early civilizations were about astronomy just by using the sun. And kind of on to probably not the next step, but another important step of observations of the sun in history. For a very long time, the only information we could collect about the sun was through the naked eye, and I feel an obligation. Please don't look at the sun with your naked eye, please. Some of the smartest minds in history have done that, like Isaac Newton, and he went blind for a couple days, so don't do that. But just by looking at it in the sky, that was kind of the only information we could gather for quite some time. Upon the invention of the telescope, however, we were able to learn a lot more. These drawings you see here were done by astronomers. I believe the one on the right was done by Galileo, who was kind of the first person to use a telescope for astronomy, because upon their invention, they were not used to look at stuff in the sky, but he had the bright idea to do that. And then I couldn't find a name on the one on the left, but it was a German physicist who the drawings are both documenting sunspots. And sunspots are a really big step towards understanding things about the sun. Not necessarily things they could glean back then, but I mean, getting the ball rolling with those observations was huge. And we'll talk about sunspots a little more later. And I kind of want to talk about modern observations too, maybe just as an excuse to put these really cool pictures here. But modern advances in technology have provided astronomers with amazing tools to observe the sun and stars in general. And that combined with very complex and arduous math and physics has given us a really, really good idea of what makes the sun tick, or maybe flicker is a better word. For instance, the image on the left taken by the Inouye, I believe that's the right way to pronounce it, solar telescope shows convection zones on the surface of the sun, which is another thing we'll talk about later. And you can see each of those granules in the diagram on the left, the kind of close up, are the size of Texas, which is pretty mind-boggling to me. Additionally, like I said earlier, the Parker Solar Probe is currently traveling towards the sun, and it's kind of going to do like a slingshot volley off of Venus. It's going to do it a couple times and get closer every time. It is currently traveling towards the sun to take highly precise measurements of particles coming off of the surface and magnetic fields coming off and the sun's upper atmosphere. And it's really going to give us some amazing insight into even further how the sun works. So now that we know that we have the tools to know so much about the sun, I want to take a little bit of a deeper dive into what we do know about it. So Our sun formed about 4.5 billion years ago when a spinning cloud of gas, like we talked about earlier, the solar nebula, condensed into a disk due to its own gravity. And this is a lot like other stars. Along with the sun itself, this cloud of gas eventually formed the planets. Like I said, we'll probably talk about that in another episode. And as well, asteroids and comets and things like that in the solar system. By composition, the sun is about 75% hydrogen, 24% helium, and 1% other heavier elements, which are formed by that nuclear fusion in the core, and also they're just available when the sun was forming. These are mainly like oxygen, carbon, iron, and weirdly enough, in astronomy, we call these metals, but even though only one of those is a metal, but for simplicity, we just call everything other than hydrogen and helium metals. So the sun is a G2 type star, putting it on the main sequence, and it is about 330,000 times more massive than the Earth. It accounts for over 99.5% of mass in the entire solar system, and it is pretty bright in the grand scheme of things. I mean, obviously there are a lot of stars that are a lot brighter than it, but it's a pretty bright star, and it kind of glows in that yellow white that we see. And because the sun burns a bit hotter than the typical red star, which is actually the most common type of star in the Milky Way galaxy, it shines brighter than 85% of the stars in our galaxy, which I thought was really interesting. So now that we've got some general information, I kind of want to break the sun into a couple different parts because there are a bunch of layers that are really cool to talk about. So the sun and all stars along with it have really complex structures caused by different densities and pressures and temperatures throughout the structure, the interior of the star. The outermost kind of like, it's almost like the outer edge of the atmosphere is called the corona, which means crown in Latin, and you might be able to see why. So the solar corona is a large extension off of the surface of the sun that is composed of really, really hot plasma, which is kind of like a gas, except the charges move freely. It's just really, really hot. The corona stretches millions of miles into outer space. It's kind of jarring to see how far it goes off of the surface of the sun in that picture. And it is really hard to see without special instruments or an eclipse happening, which doesn't happen very often, because it's just so much less dense than the rest of the sun, and it doesn't produce or reflect a lot of light. So we have to take those opportunities when we get them. Eclipses are a really big chance for astronomers to look at the corona and learn about it. And they've just got a short amount of time, so they kind of have to make it count. What makes the solar corona so hot is an ongoing study for astronomers, but recent research suggests that it's the result of things called nanoflares, which are small ejections of really energetic particles on the surface due to magnetic field lines reconnecting, and that heats the gas that's kind of off of the surface of the sun. But it's so hot, it's like factors hotter than the actual like visible surface of the sun, which we'll talk about here in a bit. The next layer of the sun is the chromosphere, which means color sphere in Latin. And it's called this because it's not exactly what we see when we look at the sun, but it's part of that surface, and you can see it when eclipses happen also. And it kind of gives it that red color that we associate with it, because it does look red when you look at it during an eclipse. The chromosphere is a really, really thin, extremely low density kind of shell of gas that sits atop the more dense center layers of the sun. And it is this is a really crazy number. It is approximately 1/100 millionth of the density of Earth's atmosphere, which is kind of crazy because we look out and we see that solid ball of gas out, well, solid is not the right word, but kind of fixed ball of gas out there. But it's way less dense than Earth's atmosphere. And the temperature of this layer varies very widely, going from about 6,000 degrees Fahrenheit to about 10,000 degrees Fahrenheit as you travel inwards towards the core of the sun. And it's approximately 2,500 miles deep, somewhere around there, and it's one of the thinner layers of the sun's atmosphere, like I said before. The next layer of the sun is the photosphere, which is perched directly below the chromosphere, and it's called the photosphere, which means light sphere in Latin, because the light emitted by the sun comes from that layer. Like when we look at the sun, we're seeing that layer. Like I said, it's the sun's visual surface is what they say, as it is the source of the light that's emitted. Well, it's not where the light came from, but it's where it comes from when we see it. And it is what we see when we look at the sun any regular time, not during an eclipse. It's blocked during an eclipse, but when you just look at it, like, well, I'm not going to set a bad example and look at the sun, but don't do that. So the temperature of that layer is about 5,777. Jessica, maybe you can, that sounded wrong when I saw it when I was doing the research for the show. Isn't there like another 5 in there somewhere? Or is that
No, that's in Kelvin.
Oh, that's in Kelvin. Okay, 5,777 degrees Kelvin, rather. Yep, thank you.
So
Which
for
is,
those who don't know Fahrenheit, that's about 10,000 degrees Fahrenheit.
yeah, which makes sense because it's at the bottom of the chromosphere, which is 10,000 at the lower layer. Yeah, so that's 10,000 degrees Fahrenheit, which is what we call like the surface temperature of the sun. And the photosphere is made up of granules, like we saw earlier with the like the Texas-sized image from the sun, and each of those are about 600 miles in diameter. They're extremely massive that rise and fall as they cool, kind of like boiling water, and they move at about 15 miles an hour, which doesn't sound very impressive because we go a lot faster than that in our cars, but 15 miles an hour for a huge blob of gas like that is kind of mind-bending to me. On the surface of the photosphere, we also see these sunspots that I mentioned earlier, which are areas much, much cooler than the surrounding material. Varying strengths of the sun's magnetic field and kind of local points on the surface prevent that those granules of material from moving back down so they can get heated again. That material just kind of stays in place for a bit and it gets really cold, like all of the other material would if it didn't sink back down. And since it gets really cold, it's not as hot, it's not emitting light in those areas that we saw earlier, like other areas of the surface of the sun. Like it just gets really cold and they're massive. You can see here the approximate size of the Earth compared to some pretty mid-range sunspots. They're really cool to see, and that was what Galileo and the other astronomer were kind of taking note of when they were making those first solar observations.
And just to clarify, I know he said that it gets really cool, but it's still very, very, very hot.
Yeah, just a lot cooler than the stuff around it.
Yeah, those darker sunspots are probably more like 7,000 degrees Fahrenheit instead of the 10.
Yeah, not like pleasantly cool, still burn you cool or hot. So the next layer of the sun, this is really cool, I like talking about this, is the convection zone, which is a really turbulent layer of those granules, those plasma blobs that I talked about, that move pretty wildly between the layer below it, which is called the radiation zone, and the photosphere. So the convection zone is 125,000 miles thick, and it can reach temperatures of 3.5 million degrees Fahrenheit, which is so crazy. And as we can see, the temperature of the sun is beginning to rapidly increase as we get closer to the center. And heat generated in the layers below the convection zone travels through this layer from the bottom to the top via convection. So like, I think the next slide, I believe, is a video kind of explaining it, but it's like boiling water in a pot. So when a bubble comes up to the surface, that hot air gets expelled and that it kind of locally cools down, and then that water that got cooled down sinks back to the bottom, and then it heats up because it touches the burner again, and then it rises back up. And that's the process that is carrying these plasma blobs from the center layers of the sun to the outer layers. Yeah, this is the video. This is really cool. They did like a kind of example of it in a saucepan. Here we go.
Energy is produced in the core of the sun through nuclear reactions. Small nuclei combine to form larger nuclei in nuclear fusion and release energy in the process. That energy then makes its way toward the surface of the sun. There are three major modes of thermal transport: conduction, convection, and radiation. This is our second video looking at thermal transport in the sun, and will specifically study convection, which is the dominant mechanism in the outer part of the sun. Convection is the actual movement of material in fluids due to buoyancy. Hotter material has relatively lower density, and thus it rises, much like a hot air balloon. Cooler material has higher density, and thus it sinks. We can easily illustrate convection with the following equipment: hot plate, small pan, silicone oil, and aluminum powder. We simply place our silicone oil and aluminum powder mixture into the frying pan and heat. It is possible to ignite the oil, so one wants to know the safe temperature range for the specific type of oil that they are using. Very high temperatures are not needed in this demonstration, and I have set the thermostat for 350 degrees Fahrenheit. As the oil heats up, convection cells are created. Hot material, initially in contact with the bottom of the pan, moves upward and boils over. Cooler material then circulates downward. The aluminum powder serves as a tool that allows us to see the circulation. Here you can see two screens with a visible image on the left and an infrared image on the right of the convection cells in the silicone oil. Realize that in the infrared image, temperature is indicated by color. The white and bright yellow regions are hotter, while the dark and lavender regions are cooler. So material we saw moving upward in the visible video is shown to be hotter in the infrared image, while material circulating downward is cooler. Convection like this on the surface of the sun is known as granulation. The material that is moving upward at several kilometers per second toward the surface appears brighter, and the cooler material moving downward is darker, giving the sun this mottled appearance. Convection cells on the sun are about 1,000 kilometers in diameter. Let's look at a fun example of convection commonly.
All right, we don't need to watch any more of that, but I think that was a really cool way of illustrating it by showing it like just in a practical example. And you can see that hot material kind of bubbles up like it would in a pan, and then it kind of falls around the side of those convection blobs as it cools down. So that's how that energy is transported from the core of the sun to the, well, not the core, but the lower layers of the sun to the outer layers of the sun. It takes a couple skips to get past the video. There we go. Alrighty, so the final layer of the sun before the core itself is called the radiation zone. And radiation zone is the region where light emitted by the nuclear fusion at the core is constantly colliding with very dense plasma and gas, and it very, very slowly works its way outwards towards the photosphere. So the upper layer of the radiative zone is about 3.5 million degrees Fahrenheit. Like we said, the lower layer of the convective zone, high layer of the radiative zone. But then once you get closer to the core, towards the end of the radiative zone, it turns to about 12 million degrees Fahrenheit. And I apologize for this image quality. I couldn't really get it to look better, but I think it's the best diagram of what happens. So the light that comes from the nuclear reaction at the core takes what's called a random walk through this really, really dense zone of gas and plasma, and it heats up that material as it goes, and until they reach the convective zone, after which they leave the star really quickly. But this random walk takes a long time, like in the range of thousands of years. The estimation is that the average random walk is 30,000 years, and light travels really fast. So you can imagine how much it's bouncing around in there, going back and forth. It's just that the kind of average direction that the light goes is outwards, but it's going all around, getting mixed up with all that stuff, and it takes 30,000 years traveling at light speed to get out of the sun, which is amazing to me. And the final layer we have is the core, where that thermonuclear process creates that radiation, and it makes a lot of heat and energy, unlike any source we have here on Earth. The core of the sun burns at about 27 million degrees Fahrenheit, which is by and large the hottest location in the solar system. And it is so hot because the pressure of the material on top pushes down so much, and it becomes so like pressurized and kind of closed in that core that everything's just moving so fast, and that's what enables that reaction to take place. So here we have the final video. This one's a little bit shorter, and it explains really well, I think, how that process powers the sun.
If we could open up the sun, we'd see layers of dense hydrogen gas, hundreds of thousands of miles deep. And at its center, the core, the sun gives birth to light. forged in one of the most violent reactions in the universe, nuclear fusion.
The specific nuclear reaction that powers the sun is fusion of hydrogen into helium. You take two hydrogen atoms, you ram them together, and what's left over is a helium atom.
It sounds simple enough, but it's not.
It's actually hard to get two atoms to fuse. Two protons have the same charge. They're both positively charged. They want to repel each other.
Protons don't like to get close together. They have to come together with a huge amount of energy or velocity to get close enough to begin to fuse. And that's very, very rare.
To force protons together takes immense amounts of heat and pressure generated by the invisible hand of gravity. The sun contains 99.8% of all the matter in the solar system. That's a lot of mass. All that mass pulls the sun together with unimaginable gravitational force.
With gravity crushing things down, things get close enough together, and nuclear fusion happens.
In this nuclear compactor, hydrogen atoms slam together 100 million quadrillion times each second. Some of these collisions are so powerful that atoms fuse, releasing energy.
When the protons come together, to bind together, they lose a little bit of mass, and that mass gets converted into energy. And every second of every day, about 5 million tons of stuff is being converted to energy. It's amazing.
All right, and that energy that he's talking about there is coming out in the form of light for the most part. So that's where all of that light comes from. It originates in the core of the star, and then, like we said, kind of takes that random walk out of the star, and then leaves the surface of the sun, and then goes all through the solar system. And that's what we see when we look in the night sky, or not the night sky. That's kind of the antithesis of what I'm talking about, the daytime sky. Now I want to talk about like the lifespan of the sun and how it started and where it's going to end up. So the sun has been burning for, like I said, about 4.5 billion years. And it's going to live for probably another 5 billion years until it's fused all of that hydrogen at its core into helium, after which it will begin to expand into a red giant star. At that point, it will be large enough to envelop the orbits of Mercury, Venus, and even possibly Earth. So for a couple 100 million years after that, it will burn helium at its core and kind of slowly shrink into a white dwarf star as it puffs off those outer layers of gas. The remnant white dwarf will be about the size of Earth, but burn about half as hot as the core of the sun. It's going to be extremely hot, but very compact. And that is kind of how the sun will go out. There's not going to be a flash, there's not going to be a bang, there's not going to be a black hole, just kind of a slow and quiet descent into being a white dwarf, like I said, no larger than Earth, radiating what energy it has away until it has none left to give. White dwarfs aren't really like other stars because they're not made out of the same type of materials. And so because of this, they don't do that fusion at the core. So that means that the time it takes for the star to exhaust its energy is a lot longer. So that white dwarf is going to be there for a long time. So like I said, for that long time after, the sun will be just kind of a quiet, small white dwarf, slowly expelling its energy and illuminating that gas that got shut off around it. And when those stars die that way, they make really pretty nebulas that I maybe should have grabbed a picture for. But like if you ever seen the Orion Nebula or the Crab Nebula, those are all kind of the results of things like this. So the sun's going to go out probably in a very pretty way. That is all I have. So I'm going to close my presentation. There we go.
Remember to unmute myself on the stream. Very cool. The sun is fascinating. Like stars in general. I don't think.
Yeah, I feel like it kind of gets taken for granted just because there's like black holes and white dwarfs and a lot of other stars, but it's really cool. It's also the only one that we've been able to get that much information about. So I think that's another thing that makes it cool is we just know a lot more about it.
Absolutely. Which of course has helped us learn about all of the others.
Yeah.
But it's really cool. All right, well, I did not see any questions that we got. Double checking again. I really wish I had 3 computer screens for this. um, yeah, I don't see any questions right now. So if anyone does have any questions about the sun, or it could be anything else, now is a great time to leave them down in the comments. And I guess we can just tell you what's coming up. Sure. All right. So for the next week, because it's almost June, our shows next week are going to be our beginning of the month shows that kind of give you a look at what's coming up in the sky for the month of June. So on Wednesday, we're going to do What's Up June edition, which is all of the different celestial events that are happening in June. And then next Saturday is our constellation show for June, where we'll tell you what stars and constellations are up, some of the stories behind them, and tips and tricks to help you find those stars and constellations yourself. We are still doing our private virtual shows if anyone is interested. You can find more information about that on our website. And we have some awesome new t-shirts that are available now. You can find a link to that in the video description. And shout out to Big Frog for helping us out with this. That retro, let me see, let me pull it back up. The far left, that design came from Big Frog, and it seems to be a favorite. I know I really, really like that one. So shout out to them for hosting the online site and for helping us come up with some of these designs. All right. Well, I keep looking down because I'm used to looking for comments on my phone, although it's sitting right in front of me on my screen. I'm not seeing any more questions or any questions, so I'm going to take that as you did an awesome job, Eli, and no one has any questions because you just covered it. Oh, we just got one. Not for you, Eli. We just got asked, when will the planetarium open? So I can't give an exact answer just yet because we are still waiting on all of the final approvals. But the plan is to open this summer for private groups. So if you want to bring like your family to the planetarium for a private show, and then hopefully by the end of summer, we will open back up to the general public on a maybe not our fully normal schedule, but at least back open. And some of that wait is because we have some new things going into the planetarium, which we're very excited about, but we want to wait and reopen once all of the new stuff is in. But all information on that will be given on our social media. So short answers, kind of this summer. Can't give exact dates yet because higher ups aren't giving me answers yet. But we're working on it, and we are very excited to have people back in. I can't wait. I can't wait to run shows in the planetarium again. I'm so excited. All right. So, not seeing anything else. Just double checking. All right, so I guess we will end it there. I know it's been a beautiful day out, so enjoy the rest of the sunshine that we have today. Thank you, everyone, for coming to the show tonight and for stopping by. We do stream regularly on Wednesdays and Saturdays at 7 p.m. Central with lots of fun stuff that we do every week. So, yeah, come back and see us again. Otherwise, have a wonderful rest of your weekend, and we will see you next week. Bye, everyone.